Close your eyes for just a moment. Not yet, not until I finish this one sentence. Somewhere right now, as you breathe slowly in the quiet of wherever you are, 123 steel valves are being adjusted by invisible hands inside a chamber so old it has watched 2 world wars come and go. And through those valves, 91 million liters of water are moving, silently, patiently, inexorably from one level of the earth to another. And they have been doing this every single day for over a century, and nobody talks about it. Nobody sings songs about it. Nobody makes monuments to celebrate it. And yet without this one lock, without this one beautiful, tireless, mechanical heartbeat buried in the stone and steel of upstate New York, the entire eastern half of the North American continent would conduct its commerce very differently tonight. So settle in. Lay your head down. Let your breathing slow. Because I am going to tell you the complete and total story of the Snell Lock, and by the time I am finished, you will understand something about water and patience and the slow, grinding dignity of things that simply work, that very few people on this earth have ever been given the chance to understand. The world loves to celebrate the dramatic. We build museums for battles. We name streets after generals. We carve faces into mountains. But the real work of civilization, the true unglamorous blood and bone of human progress, has always been done by the things we barely notice. The canal lock is perhaps the finest example of this truth that has ever existed on this earth. It is not exciting the way a rocket launch is exciting. It is not beautiful the way a cathedral is beautiful. It is not powerful the way a dam is powerful, though in some ways it is all three of these things, just very, very quietly. A canal lock is essentially a controlled argument between 2 different elevations of water, and the lock keeper, or in the modern age the lockmaster and his team, are simply the referees of that argument, making sure it happens smoothly, gently, without violence, according to a schedule that has been running longer than most of the people alive today have been breathing. The Snell Lock sits along the St. Lawrence Seaway in the state of New York, near the small community of Barnhart Island, positioned between Massena and the Canadian border, in a landscape that most Americans could not find on a map if you gave them 3 guesses and a compass. This is not an accident. The greatest infrastructure in the world tends to be located precisely where it needs to be located, not where it is convenient for anyone to come and look at it. The St. Lawrence River does not care about tourism. It does not care about scenic overlooks or gift shops. It cares only about gravity and volume, and the ancient, indifferent pull of water seeking its own level across the face of the planet. And the Snell Lock exists to moderate that pull, to civilize it, to put it to work in service of the ships that need to pass through, carrying grain and iron ore and limestone, and 1,000 other materials that keep the industrial machinery of 2 nations running every single hour of every single day. To understand why the Snell Lock exists, you have to understand something about the St. Lawrence River itself, because the river is not simply a river in the way that most people think of rivers. Most rivers, when you stand beside them and watch them, are flowing water. You can see the current. You can watch a leaf drift by and understand the direction and approximate the speed. The St. Lawrence is doing all of that, but it is also something else entirely. It is the drain for the entire Great Lakes system, which means it is the outlet for Lake Superior and Lake Michigan and Lake Huron and Lake Erie and Lake Ontario. All 5 of the Great Lakes, all of that combined surface area of water, all of that accumulated snowmelt and rainfall from the vast interior of North America, it all eventually finds its way through the St. Lawrence and out to the Atlantic Ocean. The river carries more fresh water than almost any other river in the Western Hemisphere. The volume is almost impossible to comprehend, if you are standing beside it on an ordinary Tuesday afternoon in October, watching the gray water move under a gray sky with the kind of calm that only very large bodies of water in very flat landscapes can achieve. But here is the problem, and it is a problem that engineers and dreamers and merchants and politicians grappled with for literally centuries before anyone managed to solve it. Between the Great Lakes and the Atlantic Ocean, the St. Lawrence River drops in elevation. It does not drop evenly. It does not drop in one great dramatic falls that you could build a single enormous lock around and be done with the whole business. It drops in stages, through rapids and shoals and stretches of turbulent water that made the river, for most of human history, essentially impassable to large vessels. You could take a canoe through many of these sections if you knew what you were doing and were willing to accept a reasonable chance of drowning. You could not take a ship. You could not take a vessel of any commercial significance through the upper St. Lawrence without portaging, without unloading everything, carrying it overland around the difficult sections, reloading it, and continuing on. This was spectacularly, almost comically inefficient for the movement of commercial goods, and the people who needed to move commercial goods were not amused by it. The dream of a fully navigable St. Lawrence Seaway, one through which ocean-going vessels could pass directly from the Atlantic all the way to the heart of the continent, was not a modern dream. It was not born in the 20th century. It was not conceived in the age of steel and diesel engines and precision engineering. The earliest serious proposals for improving St. Lawrence navigation date to the 17th century, when French colonists and administrators looked at the extraordinary wealth of the continent's interior and understood, with the clear eyes that commercial necessity gives you, that getting that wealth out to the markets of Europe was going to require solving the problem of the river. The French built some early canals, small things, barely functional by modern standards, but the impulse was there from the very beginning. The river needed to be tamed, or at least persuaded, and human beings were going to be the ones doing the persuading. The 19th century brought better canals, higher ambitions, and the beginning of a long, complicated, sometimes acrimonious conversation between the United States and Canada about who should pay for what and who should control what, and exactly how this seaway should be built and managed. The relationship between these two countries over the St. Lawrence is one of the most politely contentious stories in North American history. These are not countries that go to war with each other. These are not countries that send angry diplomatic cables back and forth in the night. These are countries that hold very long meetings about water management and navigation rights and power generation royalties. And those meetings can last decades, and they did last decades. And through all of those decades, the river kept flowing and the ships kept struggling, and the merchants kept complaining and the politicians kept talking. What you need to understand about the St. Lawrence Seaway project, when it finally became real in the 1950s, is that it was not simply a navigation project. It was not simply about moving ships. It was one of the largest and most complex civil engineering projects ever undertaken in North America, and it involved simultaneously solving two completely different problems that happened to share the same geography. The first problem was navigation. The second problem was power. The International Rapids section of the St. Lawrence, the stretch of river that the Snell Lock is part of, had been generating intense interest for decades, not only because of its navigation difficulties, but because of its enormous potential for hydroelectric power generation. The drop in the river's elevation through this section represented an almost incalculable amount of energy that was just rushing away to the sea every second of every day, unharassed, untapped, going to waste in a world that increasingly needed electricity. The solution to both problems was audacious in the way that only mid-20th century engineering could be audacious, which is to say it was audacious without apology and without excessive hand-wringing about whether it was too big. The plan was to build the Moses Saunders Power Dam across the St. Lawrence, a massive hydroelectric generating station that would be jointly owned and operated by the Power Authority of the state of New York and Ontario Hydro. The dam would raise the water level on the upstream side significantly, solving the navigation problem by drowning the worst of the rapids and creating a long, calm pool through which ships could travel. But the raised water level would also create a head differential, a difference in elevation between the upstream reservoir and the downstream river, and that differential would push water through the turbines of the dam and generate enormous quantities of electricity. Two problems, one solution. Very elegant, at least in principle. The execution was somewhat less elegant, but vastly more interesting. To build the dam and raise the water level, engineers first had to deal with the existing communities and infrastructure that would be flooded. This is one of the darker chapters in the Seaway story, and we will come to it in time. But it is also necessary to understand that the construction of the Seaway and the power dam required the building of entirely new infrastructure, new roads, new towns, new bridges and new locks, to replace everything that was going to be drowned by the rising water. The Snell Lock, along with its companion the Eisenhower Lock, was built as part of this enormous project, and they were built to serve a very specific and very important purpose. They were built to move ships through the section of the Seaway that the dam had created, lifting them from the lower St. Lawrence level up to the higher level of the pool behind the dam, or lowering them in the opposite direction, smoothly and reliably and quickly enough to keep the commercial traffic moving without intolerable delays. Construction on the Snell Lock began in 1954 as part of the broader Seaway construction project that was proceeding simultaneously on both sides of the international border. The scale of work underway in the St. Lawrence Valley in the mid-1950s was something that the region had never seen and will likely never see again. There were thousands of workers. There were machines that seemed almost impossibly large by the standards of the day. There were engineers with slide rules working out calculations that would have made the canal builders of the previous century weep with either admiration or despair. There was blasting, constant blasting, the thunder of explosives reshaping the bedrock of the river valley, and the sound of that thunder echoed across the water and the farms and the small towns of the region for years on end. The lock chamber itself was excavated from solid rock. This is not a metaphor. The workers did not build a structure and then put it in the river. They went into the earth, into the solid Precambrian rock of the Canadian Shield, the oldest and hardest rock on the surface of the planet, and they carved out a chamber. They drilled and blasted and removed rock and drilled and blasted and removed more rock until they had an empty rectangular space of the correct dimensions. And then they lined that space with concrete, enormous quantities of concrete poured in carefully orchestrated sequences to ensure that it cured properly and bonded with the rock, and would be capable of holding back the water pressures that the lock would experience in operation. The concrete walls of the Snell Lock are massive. Standing at the edge of the lock chamber and looking down at the empty floor is an experience that makes you feel very small in a way that is not unpleasant, just honest. The lock chamber is approximately 860 feet long. This is about the length of 2.5 football fields laid end to end, and it is not an arbitrary measurement. It is the length that was determined after extensive study of existing and projected ship traffic on the Great Lakes, to be necessary to accommodate the largest vessels that would be using the Seaway, 80 feet wide, 30 feet deep. These numbers also were not arbitrary. They were the result of careful engineering analysis, of looking at the dimensions of the ships that needed to pass through, of adding comfortable margins for safety, of considering the hydraulic forces that would be at work, and then building to those specifications with precision that would be impressive even today. The gates of the Snell Lock are perhaps the most immediately impressive physical feature of the structure. They are miter gates, a design that dates back to Leonardo da Vinci in the 15th century, a design so good, so functionally perfect for the purpose it serves, that 500 years of engineering progress have essentially not managed to improve upon it in any fundamental way. Miter gates work on a deceptively simple principle. 2 gate leaves, each one hinged at one end to the wall of the lock chamber, meet in the middle at an angle, like a very large letter V pointing upstream. When water pressure pushes against them, the angled meeting point transfers the force into the walls of the lock through the hinges, and the harder the water pushes, the more firmly the gates press together. They are, in other words, self-sealing, and the more you try to push them open with water pressure, the more effectively they close. It is one of those elegant engineering solutions that makes you understand why Leonardo thought of it, because Leonardo understood beauty in mechanics, and there is something genuinely beautiful about a force that tightens a seal rather than breaking it. The miter gates at Snell Lock are enormous. Each gate leaf is roughly 45 feet tall and weighs something on the order of 400 tons. They move, when they move, with a kind of ponderous majesty that is completely at odds with their size. You would expect something that heavy to be noisy, to groan and protest its own motion. Instead, the gates move almost silently, carried on their hinges by hydraulic machinery, swinging through the water with a slow grace that seems impossible for something so massive. Watching them open or close, if you are fortunate enough to be at the lock when a ship is being processed, is one of those experiences that stops your interior monologue completely. You just watch. You forget to think about whatever you were thinking about before. The gates have that effect on people. The hydraulic system that operates the gates and the valves and all the other moving parts of the lock is itself a marvel of mid-century engineering that has been carefully maintained and selectively upgraded over the decades. When the lock was built, the hydraulic system was state-of-the-art for 1958, which means it involved carefully machined cylinders and precisely calibrated valves, and a control system that was managed from a control house at the lock site by operators who understood the system thoroughly and could respond to unexpected situations with good judgment and experienced hands. The fundamental hydraulic engineering principles have not changed since then. Water under pressure does the same things in 2026 that it did in 1958. But the monitoring systems, the sensors, the electronic controls, the communication systems that let operators know exactly what is happening in every corner of the lock at every moment, these have been updated and modernized as technology has made better tools available. Now let us talk about the water. 91 million liters. This is the number that appears in the title of this recording, and it is not a random or approximate number. It is the volume of water that must move through the Snell Lock every time a ship is processed through it in the upbound direction, which is to say every time a ship is lifted from the lower level of the St. Lawrence below the Moses Saunders Dam to the upper level of the Seaway pool above it. 91 million liters. Let us try to put that in human terms, because the human mind is not naturally calibrated to understand numbers that large in any direct and visceral way. An Olympic swimming pool contains approximately 2.5 million liters of water. So 91 million liters is approximately 36.5 Olympic swimming pools. Every time a ship goes through the Snell Lock in the upbound direction, the equivalent of 36.5 Olympic swimming pools full of water pours into the lock chamber through the valve system in the lower gates, raising the ship from the lower level to the upper level. Then the ship exits, the gates close, and the water is released through the valves in the upper gates back down to the lower level, and the lock is ready to receive the next ship. Over the course of a navigation season, which on the St. Lawrence Seaway runs from approximately late March when the ice releases its grip, until late December when the cold makes the river impassable again, the Snell Lock processes thousands of ship transits. Multiply thousands of transits by 91 million liters per transit, and you arrive at a volume of water that the mind genuinely cannot comprehend in any direct way. It is simply a very large number. What makes this movement of water remarkable from an engineering standpoint is the speed at which it is accomplished. The filling or emptying of the lock chamber, the movement of those 91 million liters of water into or out of the chamber, takes approximately 10 minutes. 10 minutes for 36.5 Olympic swimming pools worth of water to move through the valve system and fill the chamber to the correct level. This is not a miracle of modern technology. This is a direct result of careful hydraulic engineering, of the design of the culverts and valves that control the flow of water into and out of the chamber. The valves are located in culverts that run along the bottom and sides of the lock chamber walls, and when they open, water flows through them under the pressure of the head differential, the difference in water level between the upper pool and the lock chamber, and that pressure drives a very substantial flow rate. The engineering is in knowing exactly how large those culverts need to be, how quickly the valves need to open to avoid creating turbulence that would damage the ship or make it difficult to control within the chamber, and how to manage the transition from nearly empty to nearly full without creating the kind of hydraulic chaos that would make the lock unsafe or unusable. Turbulence is one of the great ongoing concerns of lock operation. When you are moving 91 million liters of water through a chamber in 10 minutes, you are moving water fast, very fast. Fast-moving water has opinions about where it wants to go and what it wants to do when it gets there. And those opinions do not always align with the preferences of the people operating the lock or the crew of the ship inside the chamber. The design of the culvert system in the Snell Lock was carefully worked out to minimize turbulence within the chamber, to bring the water in through multiple openings distributed along the length of the chamber floor, so that the rising water lifts the ship evenly rather than creating currents and eddies that push the ship sideways or fore and aft. The chamber is designed, in other words, not just to hold water, but to control the behavior of water, to discipline it into doing what is needed without doing anything else. This is very difficult. Water has been trying to do what it wants for 4 billion years, and it is very good at it. Engineering it to do something specific without doing anything else requires a great deal of humility and a great deal of care. The ships that use the Snell Lock are called Seaway Max vessels by the people in the shipping industry, a term that reflects the precise constraints that the Seaway's lock dimensions place on vessel design. A Seaway Max vessel is a ship that is as large as it can possibly be while still fitting within the lock chambers of the St. Lawrence Seaway. 2 feet wider and it cannot enter. 2 feet taller above the waterline and it cannot pass under the bridges. The shipping industry, with its characteristic unsentimental practicality, has spent decades designing vessels that are exactly as large as the locks will permit, extracting every cubic foot of cargo capacity from the available dimensions. A Seaway Max bulk carrier, the type of vessel you are most likely to see in the Snell Lock on any given summer day, is roughly 730 feet long, 75 feet wide, and carries somewhere between 25,000 and 30,000 tons of cargo. It is an enormous object. Standing at the edge of the locked chamber watching a vessel of this size enter is one of those experiences that recalibrates your sense of scale in a permanent way. The cargo that these ships carry through the Snell Lock has changed over the decades since the Seaway opened, reflecting the shifts in the industrial economy of the Great Lakes region. In the early years of the Seaway's operation, iron ore was king. The steel industry of the American Midwest was consuming iron ore at an extraordinary rate, ore that came primarily from the mines of Minnesota's Iron Range and the Canadian Shield, and those ships moved it east and south through the Seaway in quantities that seemed almost geological. Coal moved in the opposite direction, heading west and north from Appalachian coal regions to the steel mills and power plants of the Great Lakes. Grain was a constant presence, the endless bounty of the prairie provinces and the American Midwest moving toward the export terminals of the eastern seaboard. These commodities, iron ore and coal and grain, defined the Seaway's early traffic patterns and gave it its economic purpose. The years have brought changes, as years always do. The American steel industry, which was once the largest and most productive in the world, contracted sharply in the late 1970s and 1980s, a contraction that reduced iron ore traffic on the Seaway substantially. The coal industry has contracted for different reasons in more recent decades. Grain traffic has been more stable, but has fluctuated with the vagaries of harvests and global commodity markets. New commodities have emerged, potash from Saskatchewan moving to markets around the world, limestone from quarries along the Seaway corridor moving to construction sites and industrial users, wind turbine components moving in specialized vessels from manufacturing facilities to installation sites. The Snell Lock has seen all of it, processed all of it, lifted and lowered all of it with the same steady mechanical rhythm that it has maintained since the day it opened. The day it opened was April 25, 1959, when the St. Lawrence Seaway was formally inaugurated in a ceremony presided over by President Dwight D. Eisenhower and Queen Elizabeth II, the two heads of state of the two nations that had built it together. This was one of the great state occasions of the post-war era, one of those moments when the optimism and ambition of the mid-20th century was on full display for the world to see. Here were the leaders of two of the most powerful nations on Earth, standing together on a ship passing through a canal they had built together, opening a waterway that would connect the interior of the continent to the world. The speeches were magnificent in the way that speeches in that era tended to be magnificent, full of confidence and forward-looking vision, and a sense that human ingenuity, properly applied, could solve any problem and build any necessary thing. Eisenhower, who had been Supreme Allied Commander in Europe and understood something about large logistical operations, said that the Seaway represented the kind of peaceful collaboration that he hoped would define the relationship between nations in the post-war world. The Queen, representing Canada and the Commonwealth, spoke of the deep ties between the two countries and the importance of the Seaway for the economic development of both. The ceremony was broadcast on television to millions of viewers, and the images of ships passing through the gleaming new locks, the enormous gates swinging open and closed with their impossible grace, were genuinely inspiring to people who had been reading about this project in their newspapers for years, and were now watching it become real. What is less often remembered about the opening of the Seaway is what had to be sacrificed to create it. The raising of the water level behind the Moses Saunders Dam, necessary for both navigation and power generation, flooded a substantial area of land on both the American and Canadian sides of the border. On the Canadian side, entire communities were displaced. The Long Sault Rapids, which had been a landmark of the St. Lawrence for as long as anyone could remember, a series of turbulent whitewater passages that had challenged and sometimes defeated river travelers for centuries, were drowned under the rising water. They simply ceased to exist. The pools above the dam are calm now, and somewhere beneath that calm surface, under 30 or 40 feet of water, are the foundations of houses, the ruins of churches, the outlines of roads and fields and gardens that existed until the water covered them. The communities that were displaced, a collection of small towns and villages collectively known as the Lost Villages, were handled with what their residents sometimes described as efficiency, and what historians now tend to describe as the ruthless pragmatism that large infrastructure projects impose on small human communities. The people were told they had to move. New communities were built for them, planned communities with proper streets and services, in locations outside the flood zone. The old communities were systematically demolished before the flooding to prevent debris from becoming a navigation hazard, and then the water rose over the cleared land and covered it all. Some of the people who were displaced from those villages never entirely forgave the project for what it took from them, and that is entirely understandable. You can build someone a new house, but you cannot build them a new childhood, a new set of memories located in specific streets and specific views from specific windows. Those things, once drowned, stay drowned. This is one of the things that the Snell Lock carries, though it cannot feel the weight. Every ship that passes through it, every upbound transit that requires 91 million liters of water to enter the chamber from the upstream pool, draws on water that covers the land of those lost communities. The lock is physically located in the landscape that was permanently altered by the project that created it. The relationship between the lock and the lost villages is not one that appears in any engineering manual or operations procedure. It is simply a fact of geography and history, the kind of fact that sits quietly in the background of things, visible if you know to look for it, invisible if you do not. The construction period of the Seaway, from 1954 to 1958, was one of the most concentrated periods of civil engineering activity that North America had ever seen. At its peak, the construction project employed approximately 22,000 workers on the American side alone, with comparable numbers on the Canadian side. The logistics of feeding and housing and transporting this workforce were themselves a significant organizational challenge. Construction camps were established along the river, communities of workers that appeared and then disappeared as the work progressed, leaving behind only the structures they had built. The workers came from all over. There were experienced dam builders who had worked on the Colorado River projects in the American Southwest. There were miners who knew how to work in rock. There were ironworkers and concrete specialists and electricians and crane operators, and all the other specialized tradespeople that a project of this complexity required. The excavation of the lock chamber was among the most challenging operations of the entire project. The Canadian Shield bedrock is, as previously noted, among the oldest and hardest rock on the surface of the Earth. It does not yield to excavation without argument. The drilling and blasting operations required to remove the rock were carefully planned and executed to avoid damage to the adjacent structures that were being built simultaneously. Because you cannot blast carelessly when you are 30 feet away from a concrete wall that has to hold back a river. The sequencing of construction, the careful orchestration of which operations happened in what order and which crews were working in which locations, was itself a feat of organizational engineering that deserves more recognition than it typically receives. The concrete pours for the lock walls were among the largest continuous concrete placements in the history of construction to that point. Concrete must be poured continuously once a pour begins, because if you stop and the concrete begins to cure, and then you pour more concrete on top, you create a cold joint, a weak plane in the structure where the two pours meet. For a structure as critical as a lock chamber that must hold back enormous water pressures, cold joints are not acceptable. So the concrete for the lock walls was poured in carefully planned lifts, each lift completed before the previous one had fully cured, with the entire operation running continuously around the clock, in day and night and rain and cold, until each section of wall was complete. The workers did this in shifts, sleeping in the construction camps and returning to work every 8 hours, maintaining the rhythm of the pour the way a team of riders maintains the rhythm of a relay race. The instrumentation that monitors the Snell Lock today would be utterly unrecognizable to the engineers who built it. In 1958, the monitoring of a lock's condition was largely a matter of visual inspection and the experienced judgment of the operators who worked there every day. They could tell you whether a gate was sealing properly by watching the water. They could tell you whether a valve was operating correctly by listening to it. This kind of intimate, embodied knowledge of a machine is not nothing. It is in some ways more valuable than any sensor reading, because a person who has worked with a machine every day for 10 years understands its normal behavior so thoroughly that any deviation from that behavior registers immediately, before any instrument has a chance to record it. But modern monitoring systems add layers of objective measurement that the human senses cannot provide. Sensors track the position of gates and valves with millimeter precision. Strain gauges measure the forces on critical structural members. Water pressure sensors track conditions throughout the hydraulic system. Cameras provide visual coverage of every part of the operation. All of this data flows to a control room where operators who have been thoroughly trained and who have extensive experience with the system can see everything that is happening at once. The navigation season on the St. Lawrence Seaway operates on a schedule that is dictated by weather and ice rather than by any human preference. The river freezes in winter. This is not a gradual or negotiable process. The temperatures in the St. Lawrence Valley in January and February are genuinely brutal, the kind of cold that forms ice quickly and thickly on standing water, and the St. Lawrence, for all its size, is not immune to this process. The Seaway Authority closes the Seaway to commercial traffic in late December, when ice conditions make navigation unsafe, and reopens it in late March, when the winter ice has cleared sufficiently to allow ships to move safely. This gives the navigation season roughly 9 months, and during those 9 months the locks must be as available and reliable as humanly possible, because every day of unplanned downtime represents ships that are not moving and cargo that is not being delivered and commerce that is not happening. The winter months, when the lock is not handling ship traffic, are not idle months. They are, in fact, extraordinarily busy months from a maintenance standpoint. The closure of the navigation season is the only extended opportunity that the lock maintenance crews have to inspect and repair the parts of the lock that are normally submerged, the lower portions of the gate leaves, the underwater valves and culverts, the sill on which the gates rest when they are closed. To access these parts, workers must first pump the water out of the lock chamber, a process that itself requires careful coordination with the upstream water management. Once the chamber is dewatered, workers in waders and boots descend to the floor of the chamber, which is normally 30 feet below the water surface, and begin the painstaking process of inspection. They are looking for cracks in the concrete, for corrosion on the steel components, for wear on the gate hinges and valve seats, for any sign of damage or deterioration that could affect the lock's performance or reliability during the coming navigation season. What they find is usually a combination of expected wear and occasional surprises. The expected wear is managed through planned maintenance programs, replacement schedules for components that have known service lives, regular inspection cycles that catch developing problems before they become serious problems. The surprises are managed through the kind of engineering judgment and field improvisation that experienced maintenance crews develop over years of working with complex hydraulic structures. Sometimes a surprise is minor, a crack in a concrete section that needs to be epoxy injected before it propagates further. Sometimes a surprise is more significant, unexpected corrosion on a structural steel component, a bearing that has worn faster than anticipated, a seal that has failed in an unusual way. These surprises keep the winter maintenance season interesting, if interesting is the right word for the kind of problem solving that happens at the bottom of a dewatered lock chamber in January in upstate New York. The gate leaves themselves are the components that receive the most anxious attention during winter maintenance, and for good reason. The gate leaves are the primary structural elements that hold back the upstream water from the downstream river, and if one of them were to fail in service, the consequences would be immediate and severe. Each gate leaf is essentially a very large, very carefully engineered steel box, hollow inside to provide buoyancy that reduces the load on the hinges, with carefully designed flanges along the mating edges where the two leaves come together. The steel is painted with protective coatings that must be regularly inspected and renewed, because steel in a wet environment, steel that is alternately submerged and exposed to air, is constantly under attack from corrosion. The coatings keep that attack at bay, but only as long as the coatings are intact, and they develop defects over time through mechanical damage and the normal degradation of organic coatings in service. The hinges, called quoins and heel posts in the technical vocabulary of lock engineering, are the points where each gate leaf connects to the lock wall. These are the most highly stressed components of the gate system, the points through which all the hydraulic forces pass from the gate into the wall. They are designed with generous safety factors and are made of the best available materials, but they are still mechanical components that experience cyclic loading every time the gate opens and closes, and cyclic loading over enough cycles eventually causes fatigue. The maintenance crews who inspect the quoins during the winter are looking for the early signs of fatigue, the micro cracks and surface irregularities that precede visible damage, and they find them sometimes. And when they do, they take corrective action before the fatigue progresses to actual failure. This is the quiet, unglamorous work that keeps the lock running year after year, the work that happens in the cold and the dark at the bottom of an empty chamber, while most people are finishing their holiday shopping or watching football on television. The lock operators, the people who actually run the Snell Lock on a day-to-day basis during the navigation season, are in some ways the human embodiment of the lock's essential character. They are extraordinarily competent at something that most people do not know exists. They understand hydraulics and vessel handling, and radio communication and emergency response, and the meteorological conditions of the St. Lawrence Valley with a thoroughness that comes only from years of daily practice. They work rotating shifts because the lock operates around the clock during the navigation season, and they bring to each shift the kind of focused, calm attention that complex and safety-critical operations require. They are not dramatic. They do not perform. They simply do their work with a quiet professionalism that is entirely appropriate to the work they are doing. A typical ship transit through the Snell Lock, from the moment the vessel enters the outer approaches to the moment it clears the far end of the chamber and continues on its way, takes somewhere between 45 minutes and an hour. This includes the time for the ship to approach and enter the lock chamber, the time to close the gates behind it, the time to fill or empty the chamber, the time to open the gates on the other side, and the time for the ship to depart. The ship's crew has roles in this process, managing the mooring lines that hold the vessel in position within the chamber as the water level changes. The lock crew has roles, monitoring the hydraulic system, communicating with the ship's crew, managing the gate and valve operations. It is a coordinated operation that has been refined over 60-some years of continuous practice until it runs with a smoothness that makes it look simpler than it is. The mooring lines deserve a brief digression because they are one of the aspects of lock operation that surprises people who learn about it for the first time. When a ship enters a lock chamber, it is a very large object in a relatively small space, and as the water level rises or falls, the ship must be held in position so that it does not drift toward the walls of the chamber or the gates. The way this is done is with mooring lines, heavy wire or fiber ropes that run from the ship to bollards on the lock wall, controlled by the ship's deck crew. As the water rises, the crew must pay out line, letting the ship rise with the water level while maintaining tension in the lines to keep the ship in position. It sounds simple. In practice, on a vessel 700 feet long and a chamber 80 feet wide, with the turbulence of 91 million liters of water entering the chamber through the culverts below, it requires careful attention and good judgment. The lock crew is watching, ready to communicate with the ship if anything looks wrong, ready to slow the filling rate if turbulence is causing control problems. The St. Lawrence Seaway Authority, the joint Canadian-American body that manages the Seaway, maintains detailed statistics on lock operations, because detailed statistics are the language in which infrastructure systems speak about themselves. Vessel transits per year, tons of cargo per transit, average transit time, downtime for maintenance and unplanned outages. These numbers tell the story of the Seaway's economic health and operational reliability in a language that engineers and administrators understand instinctively. The numbers for the Snell Lock are, in the dry vocabulary of operation statistics, good numbers. The lock runs reliably. It processes the traffic it is presented with. It meets or exceeds its performance targets in most years. In the language of infrastructure, this is the highest possible praise. The power relationship between the Snell Lock and the Moses Saunders Power Dam is one of the subtler and more interesting aspects of the lock's operational context. The dam and the lock are not independent structures. They share the same water, the same elevated pool upstream and the same lower river level downstream, and decisions made about one affect the other. The dam operators, managing the flow of water through the turbines to generate electricity, must take into account the needs of the lock operators, who need a certain minimum water level in the upstream pool to safely operate the lock. The lock operators, when they fill the lock chamber from the upstream pool, are temporarily drawing down that pool by a tiny amount, a completely negligible amount given the scale of the reservoir, but one that must be accounted for in the overall water management equations. These interactions are managed through coordinated operating protocols developed over decades of joint operation, and they work well enough that most people involved in either operation rarely need to think explicitly about the other. The generation of electricity at Moses Saunders is itself a story that deserves to be told, though it is somewhat adjacent to the story of the Snell Lock. The dam has 32 generating units, 16 on the American side and 16 on the Canadian side, and at full capacity, it generates approximately 2,000 megawatts of electricity, enough to power a substantial number of homes and businesses. The American half of that output goes to the New York Power Authority, which distributes it across the state with a preference for supplying power to businesses and industries in the region near the dam, a preference that has attracted manufacturing and other energy-intensive industries to the region, and has been a significant factor in the economic development of the St. Lawrence Valley. The Canadian half goes to Ontario Hydro, and from there into the Ontario electricity grid. The dam has been generating this electricity continuously since 1958, and the revenue from that generation has helped pay for the ongoing operation and maintenance of both the dam and the locks. There is something almost meditative about thinking of the relationship between the electricity and the lock. The same water that lifts the ships in the Snell Lock is falling through the turbines of the dam a few thousand feet away, turning generators, producing electrons that flow down transmission lines to light homes and run factories, and charge the devices on which people are perhaps right now listening to this very story. The water is doing both things simultaneously, serving navigation and serving power generation. And when you understand that, when you really sit with that understanding, the engineering of the Seaway takes on a quality that is almost philosophical. It is the optimization of a natural resource, the extraction of maximum useful work from the energy that was always present in the river's fall from the upper elevation to the lower, work that, before the dam and the locks, simply radiated into the turbulent white water of the international rapids and was lost. The wildlife of the St. Lawrence corridor has complex relationships with the Seaway infrastructure. The river is a major migration corridor for fish, and the dam presents what is called in fisheries management a passage barrier, an obstacle that fish cannot cross when swimming upstream to spawn. This is a significant ecological concern for several species, including Atlantic salmon, which historically used the upper St. Lawrence and some of the Great Lakes tributaries for spawning, and which were effectively extirpated from those habitats by the combination of the dam, habitat alteration, and overfishing that characterized much of the 20th century. Efforts to restore Atlantic salmon to the upper St. Lawrence have been ongoing for decades, with mixed results, and the presence of the dam and its associated structures continues to be a complicating factor in those efforts. Fish passage facilities have been studied and in some cases implemented, but the engineering challenges of moving fish through or around a structure as large and energetically powerful as Moses Saunders are genuinely formidable. The bird life of the lock area is, by contrast, largely indifferent to the human engineering that surrounds it. The lock walls and the approach walls that extend on either side of the lock chamber provide excellent perching and nesting sites for a variety of species. Cormorants, which have expanded dramatically in the Great Lakes and St. Lawrence region over the past few decades, are particularly fond of the lock structures, using the approach walls as roosting sites when they are not hunting in the river. Great blue herons stand in the shallows at the edge of the lock approaches with the sculptural patience that defines their species, waiting for fish to come within striking distance. Osprey hunt over the open water of the upstream pool, diving feet first in the spectacular plunge that makes them one of the most exciting birds to watch in the region. None of these birds care about the history of the Seaway project or the engineering of the lock hydraulics. They care about fish and safety and a place to rest, and the lock provides all three. The ice management challenges of the navigation season's beginning and end are worth dwelling on for a moment, because they are one of the less obvious operational challenges of the lock. At the opening of navigation in late March, the river is often still carrying ice, large slabs of it broken free from the winter ice cover and floating downstream on the spring current. These ice flows must be managed carefully as ships approach and enter the lock, because a large piece of ice caught under a gate leaf as it closes could prevent the gate from seating properly, causing it to leak and potentially preventing lock operation. The lock crews develop protocols for managing ice in the approaches, and the ship's crews understand the hazards and cooperate in managing them. In difficult ice years, the opening of navigation is delayed until conditions are safe, regardless of the commercial pressure to start the season as early as possible. At the end of the season, the challenge is the transition from open water operation to closure. The lock must be properly secured for the winter, which means ensuring that all the systems that could be damaged by freezing temperatures are either drained or protected against frost damage. Water left in pipes and culverts will freeze, and water expands when it freezes, and that expansion can crack pipes and valves and cause damage that requires expensive repair. The closure procedures involve systematically going through every water-containing component of the lock system and ensuring that it is either drained or winterized, a process that takes several days and requires careful checklisting to ensure nothing is missed. The navigation season of 1959, the first full navigation season after the Seaway opened, was in some ways the most exciting and in other ways the most chaotic period in the lock's history. The new infrastructure was meeting real commercial traffic for the first time, and there were inevitably teething problems. Equipment that had performed perfectly in testing sometimes behaved differently under the sustained demands of actual operation. Crews that had been trained on the equipment discovered that there were things about actual operation that training had not fully prepared them for. The shipping companies whose vessels were using the new locks were discovering the practical realities of Seaway Max navigation. The precise maneuvering required to enter an 800-foot chamber with a 700-foot vessel. The care required in the unfamiliar hydraulic environment of the filling chamber. Everyone was learning, from the lockmaster down to the line handlers, and the learning happened in real time with real ships and real cargo, which concentrates the mind wonderfully. The accidents that occurred in the early years of Seaway operation were mostly minor, groundings in the channel approaches, minor collisions with the lock walls, equipment malfunctions that caused delays but not disasters. There were occasional more serious incidents, groundings that required salvage operations, equipment failures that required extended shutdowns for repair. Each incident was analyzed in detail by the Seaway Authority and by Transport Canada and by the U.S. Army Corps of Engineers, which has regulatory responsibility for certain aspects of the American navigation infrastructure. And the lessons from each incident were incorporated into operational procedures and training programs. This is how complex systems learn. They learn from their failures, if the people responsible for them are willing to look honestly at what happened and why, and the Seaway Authority over the decades has generally been willing to do that. The relationship between the Snell Lock and the shipping community that uses it is best described as one of mutual respect and mutual dependence. The shipping companies depend on the lock to be available when they need it. The lock depends on the shipping companies to send it traffic that justifies its existence. This mutual dependence has produced, over time, a relationship that is collaborative in a pragmatic rather than a sentimental way. When the lock must close for emergency maintenance, the Seaway Authority communicates with the shipping companies as quickly and as fully as possible, giving them the information they need to make routing decisions. When ships arrive in poor condition or with inadequately trained crews who create operational problems, the lock management works with the shipping company to address the issues. The relationship is professional, functional, occasionally tense, and generally productive. The role of the Snell Lock in the broader North American supply chain is almost impossible to overstate, though it is almost universally understated in the public discourse about supply chains and economic geography. When people talk about supply chain vulnerabilities in the wake of the disruptions of the early 2020s, they talk almost entirely about ocean shipping and container ports, and the big vessels that cross the Pacific and Atlantic. They rarely talk about the inland waterway system, about the locks and canals and river systems that move bulk commodities through the interior of the continent, with an efficiency that no other mode of transport can match for those specific types of cargo. Water is the cheapest way to move bulk goods. It has been the cheapest way since before recorded history, and the economics have not changed in any fundamental way. Only the scale of the vessels has changed, and the locks that accommodate those vessels. A single Seaway Max bulk carrier moving grain from a Lake Superior port to the St. Lawrence Seaway grain terminals near Montreal carries as much cargo as approximately 600 semi-trailer trucks. 600 trucks. The fuel consumption per ton-mile of water transport is a small fraction of the fuel consumption per ton-mile of road transport. The carbon emissions per ton-mile of water transport are correspondingly lower. For the movement of bulk commodities, grain and iron ore and coal and potash and limestone, water transport is not merely competitive with road and rail transport. It is decisively superior on both economic and environmental grounds. And the Snell Lock is one of the gateways through which all of that water transport must pass, one of the unavoidable choke points in a supply chain that serves the agricultural and industrial heartland of North America. This gives the Snell Lock a kind of silent power that is entirely out of proportion to its profile in the public consciousness. It is not famous. It does not appear on the news. It is not the subject of popular culture references. But if it were to stop functioning, if some catastrophic failure were to close the Snell Lock for an extended period, the effects would ripple through the North American economy in ways that would eventually become visible to people who have no idea where the St. Lawrence Seaway is and could not identify the Snell Lock on any map. Grain prices would move. Steel prices would move. The long, invisible threads that connect the lock to the everyday economy would go taut and then snap, one by one, until the disruption reached the grocery store shelves and the factory production lines, where people would finally notice that something, somewhere, had gone wrong. The people who designed and built the Seaway understood this. They understood that what they were building was not just infrastructure. They were building a critical piece of the economic system of an entire continent, and they built it accordingly, with conservative safety factors and generous margins, and the assumption that it would need to last for a very long time. 70 years on, that assumption has proven correct. The Snell Lock is not new. Some of its components are original, dating to the construction in the 1950s, maintained and refurbished but fundamentally unchanged from what was put in place during that extraordinary construction period. Other components have been replaced, upgraded, improved. But the essential structure, the lock chamber cut from the ancient rock of the Canadian Shield, the concrete walls that contain it, the basic hydraulic architecture of the culverts and valves, these endure, doing what they were designed to do with a reliability that justifies every dollar and every hour that went into building them. The question of what comes next for the Snell Lock, and for the St. Lawrence Seaway more broadly, is one that engineers and policymakers and shipping industry representatives have been discussing with increasing urgency in recent years. The locks of the Seaway were designed for a maximum vessel size that seemed very large in 1958. By the standards of modern ocean shipping, they are not large at all. The post-Panamax container ships and bulk carriers that now dominate ocean trade could never enter the St. Lawrence Seaway. They are simply too large, too wide, too deep in the water. This size constraint means that the Seaway is effectively disconnected from the trends that are shaping global maritime commerce, the push toward ever larger vessels that can spread fixed costs across ever larger cargo loads. The Seaway has its own size category, the Seaway Max, and it will always have that size category unless someone builds new, larger locks, which would be an undertaking of extraordinary complexity and cost. The discussions about the future of the Seaway infrastructure acknowledge this constraint and wrestle with what, if anything, should be done about it. Some argue that the Seaway should be upgraded with larger locks, allowing the passage of larger vessels and reconnecting the Great Lakes ports to the full scale of global maritime commerce. Others argue that the current lock size is adequate for the types of cargo that the Seaway handles, bulk commodities that are not well suited to the container shipping model anyway, and that the capital investment required for lock enlargement would not produce adequate return. These are not simple questions, and they do not have simple answers, and the discussions continue with the measured pace that major infrastructure decisions require. What is certain is that whatever happens next, the Snell Lock will be part of it. It cannot be bypassed. The geography that required it in 1958 still requires it today. The river still drops in elevation at this section. The ships still need to be lifted from the lower level to the upper level or lowered in the opposite direction. The physics have not changed, and so the lock will continue to do what it has always done, processing ships one at a time through its chamber, moving 91 million liters of water each time with the quiet efficiency that has defined its entire operational history. There is something deeply comforting about this when you sit with it long enough. In a world that seems to change almost faster than the human mind can track, that produces news and disruption and novelty at a rate that can feel genuinely overwhelming, there are these structures, these patient mechanical systems, that simply continue. The Snell Lock does not care about what is trending on the internet today. It does not care about the political arguments that are occupying the attention of the people who live near it. It cares about ships that need to be lifted and water that needs to be moved and gates that need to open and close on schedule. It has cared about these things every day for 60-some years, and it will continue to care about them tomorrow, and next week, and next season, and for as many seasons as it remains structurally capable of doing so. The rhythm of the lock, the rhythm of a ship approaching, entering, being lifted or lowered, departing, the gates closing behind it, the chamber preparing for the next transit, this rhythm is one of the oldest kinds of human rhythm. The rhythm of useful work done reliably and well, repeated as many times as necessary, without drama or complaint. The people who work at the lock participate in this rhythm. They align themselves to it, as shift workers align themselves to the rhythms of the systems they tend, and over time the rhythm becomes part of them. The retired lockmasters who have spent decades watching ships pass through their lock carry that rhythm in their bodies, in the way they pay attention, in the quality of calm that people who have done important repetitive work for a long time tend to carry. The water, of course, carries the rhythm most completely. The water that lifts the ships in the Snell Lock today is not the same water that lifted ships in 1959. Water does not stay. It moves, as water has always moved from source to sea, from sea to sky, from sky to source again, in the eternal hydrological cycle that has shaped the planet for 4 billion years. But the function, the purpose for which the water is temporarily conscripted each time a ship enters the chamber, this remains constant. 91 million liters, lifted smoothly in 10 minutes, every transit, every day, every season. The hydrological rhythm of the Snell Lock is a tiny eddy in the vast circulation of water across the planet's surface, but it is a steady eddy, a predictable one, a human eddy shaped by human needs and human engineering, and maintained by human care. The engineers who designed the Snell Lock are mostly gone now. The workers who built it are gone. Some of the first generation of operators have retired, and some of those have died. And what they knew about the lock in the intimate physical way that you know a machine you have worked with for decades, that knowledge has partly passed to their successors and partly gone with them. The parts that could not be written down, the felt sense of normal versus not normal, the intuition that comes from thousands of hours of direct observation. This is the nature of craft knowledge, and it is one of the most poignant kinds of loss that complex technical systems experience as they age. Each generation of operators must rebuild a portion of this knowledge from their own experience, and the process of rebuilding it is the process of the lock training a new generation of people who will tend it. The archives of the Seaway Authority contain thousands of pages of operational records, inspection reports, maintenance logs, incident analyses, and engineering studies. These documents are the institutional memory of the lock, the written record of what has been done, and what has been found, and what has been decided over 6+ decades of operation. They are not glamorous reading. They are full of technical terminology and engineering measurements and procedural language. But they contain, if you are patient enough to read through them, a remarkably complete portrait of a complex machine and the human system that keeps it running. Every maintenance problem that was encountered and solved is in there. Every unusual transit, every ice management challenge, every equipment modification, every decision about whether to defer a repair or do it immediately. All of it is documented in the careful bureaucratic prose that public infrastructure agencies use, because precision matters more than elegance when the record might need to be consulted by an engineer trying to understand why something is behaving the way it is behaving. There is a particular type of peace that comes from understanding how things work, not the shallow piece of distraction, where you stop thinking about your worries by filling your attention with something entertaining. The deeper piece of comprehension, where you understand some part of the world well enough that it no longer seems arbitrary or threatening, where you can see the reasons behind the things you observe, where the machinery of existence becomes, if not simple, at least legible. The Snell Lock offers this kind of peace to anyone willing to learn about it, because it is a system whose workings can be understood, whose history can be traced, whose purpose is clear, and whose operation, once you understand it, makes complete and satisfying sense. The water rises, the ship rises. The gate opens, the ship departs, the chamber empties, The gate closes. The next ship approaches, again, and again, and again. Let the rhythm of it carry you as you listen. Let the image of the water rising slowly in the chamber, lifting the enormous ship with the same effortless authority with which bathwater lifts a bar of soap, let that image settle into you. Let the sound of the gates, the deep low sound of 400 tons of steel moving on hydraulic cylinders through water, a sound felt more than heard, let that sound become part of your awareness. Let the rhythm of the lock, the patient, ancient human rhythm of lifting and lowering, of opening and closing, of receiving and releasing, let it carry you toward sleep the way the river carries everything toward the sea, steadily and without hurry, in its own time and on its own terms. The Snell Lock is working right now. Somewhere in the navigable months of the year, at this very moment, there may be a ship in the chamber, resting against its mooring lines in the quiet of the lock, waiting for the water to rise around it, carrying grain or iron ore or limestone from one part of the continent to another, doing the invisible necessary work that keeps the world going. And the water is rising around it, 91 million liters of it, patient and certain, doing what water has always done, finding its level, filling the space that is given to it, lifting whatever rests upon it with the indifferent generosity that is the deepest nature of water. Sleep well. The lock is watching. The water is rising. Everything necessary is being done.